Hi everybody, I'm Yanwei. I'd like to introduce our paper, Learning Dynamic Routing for Semantic Segmentation. In this paper, we succeed to extend the multi-pass dynamic inference to semantic segmentation. As we all know, traditional methods utilize human-designed architectures or neural architecture search for high-performance semantic segmentation. One of the classic architecture designed by human is DeepLab V3, which uses human-designed pipeline and ASPP module to achieve better performance. With the development of neural architecture search, there are several automatic approaches for semantic segmentation. For example, auto-deploy searches in the designed space for single pass and corresponding operations. But all of the previous works for semantic segmentation are static and fixed for inference. However, there are huge scale variance among inputs. As we can see in the red diagrams, three inputs with different scale distributions may need different inference routes, because a large instance needs higher semantic context, but small instances could prefer detail-preserving architectures. Thus, inference passes should adapt to the input images, and we need dynamic routing for data-dependent architectures. Here we introduce our solution, the dynamic routing framework for semantic segmentation. As is illustrated in the figure, we do not design or search for a specific architecture, but give the dynamic routing space with low L and max downsampling rate 32. In the proposed framework, the forward inference passes will be generated in each node. That means given an input image, each node will generate data-dependent routes and transform to different resolutions according to the input features. So the proposed dynamic routing is claimed to have the superiority in network capacity and higher performance with the budgeted constraints. Then we introduce the proposed dynamic routing space to release the potential of the dynamic routing. Both the multi-scale routes as well as script connections are supported in the desired routing space, so several classic architectures can be formulated in similar forms. For example, we can model the famous fully convolutional network, the U-shaped net, the DeepLab V3, the Auto-DeepLab, and also the HRNet V2 in the dynamic routing space. And you may wonder how to select the routing passes in each node. Here we give the details. So, given the design routing space with several individual nodes, we adopt a basic cell and a gate inside each node for feature aggregation and path selection, just as the figure illustrated. Specifically, we first aggregate multi-scale feature X from the formal layer to formulate the hidden state feature H. According to the generated feature H, we choose routing passes to the next layer. First, the gating feature G will be calculated using the generated feature X, and then activating weights for different passes could be generated using activating function. We can calculate the activated feature in this node, and the features which have positive activating weights will be transformed to corresponding scales. If all the passes in this node are marked as closed, we will not use the convolutional operations in the cell, and output the input feature X directly. In this way, the computational resources could be saved in this node. Considering the limited resources in the real-world scenario, we give the budget constraint to the framework for efficient inference. We firstly calculate the per-node cost, and then we summarize the cost of all the nodes in the dynamic routing space to formulate the space-level cost. So the constraint loss could be calculated in a form of L2 loss function, which can be optimized in end-to-end manner. Then we compare with several classic architectures under similar flows and the same training settings, which are modeled using the proposed routing space. As can be seen from the table, compared with handcrafted or search architectures, the proposed dynamic routing achieves much better performance with similar resource cost. Actually, some passes are always kept with different inputs, so we define these passes as common networks, and we further give the common networks extracted from different types of dynamic networks. In fact, the common networks share a similar turn with classic architectures. Compared with previous works, the common networks still have better performance, but they are inferior to corresponding dynamic networks. To further analyze the routing framework, we give the details. From the figure, we can see that most of the passes tend to be preserved if do not consider resource cost, and different proportions of routes will be dropped if given budget constraints. The expected flops and resource cost will be optimized steadily with different budget constraints in the training stage, which matches the performance of different dynamic networks. Compared with previous works, the proposed dynamic routing achieves similar performance with much less resource consumption in different datasets. Thanks, we have released the code and pre-trained models in the following link.